Good morning, everyone, and welcome back to the talks for linux.conf.au 2022. First up this morning, we have Casey Schaufler, who will be speaking about security community expresses too many Venn diagrams. And I do enjoy a good Venn diagram, so I'm pretty excited for this one. So Casey Schaufler founded the SMAC project in 2006 after an especially heated debate with the SE Linux developers on a topic now long forgotten. He has been developing secure operating systems since the late 1980s, starting the system that became Trusted Solaris and architecting Trusted IRIX. He was the technical editor for the influential POSIX P103.1e/2c, why did I leave that in for the spoken one, security draft standard. He is currently working on the Linux security module infrastructure. So Casey will be taking questions after the talk if there is time left. So please, everybody, if you've got questions for Casey during the talk, post them in the questions tab at the top of the chat in Venulus. Note that your questions may not appear right away because it is moderated. I or one of the other volunteers will approve them. And then at the end of Casey's talk, if there's time, I'll pass them on to Casey. So thank you very much for speaking for us today, Casey. All over to you.
Thank you. My name is Casey Schaufler. I've been working in the security community for some time. I've been developing kernels since the 1970s. I've been working in security, as we mentioned, since the mid-80s. And I'm the author and maintainer for the SMAC Linux security module. So I want to put a little bit of context in place for the talk today. And the first thing I want to talk about is community. Now, you've heard a lot of talks so far in the conference about communities. And the technical definition of a community is people with something in common. But we really want to talk about community in terms of not only do the people have something in common, but they communicate with each other about it. If you don't communicate, you don't really have community. Next thing, tricky finger here. Computer security. A feeling of safety around and about computers. There are lots of technologies involved in computer security, but it really is about how security is how you feel about it. And the feeling of safety is very important in a lot of aspects. And then the third thing is a Venn diagram. Venn diagrams were invented in 1880 by John Venn, and one wonders how people described relationships between sets of things before they had Venn diagrams. Now, the other thing the Venn diagrams have actually been very useful for is that it introduced the concept of visualizing data. And we look at it now and it's like, well, of course it's simple, it's obvious, but this was a very new thing. Not that long ago. 1880 was not prehistoric times. So we're going to start off with a story. I like stories. So this story is about the birth of a community. And it takes place, or at least it starts, in Europe in the middle of the 20th century. At that time, right around 1944, the most prominent people, given that the world was essentially at war, there were soldiers, politicians, spies, and there were mathematicians who you might not normally think in terms of being the same august entities as these other groups, but we'll describe that a little bit. Now, among the politicians, there were also some of the members of politicians, but there were also spies who were politicians, and there were soldiers who were politicians. And there were some politicians who were acting as soldiers as well. So there was some overlap. The set of people who are politicians includes some soldiers and some spies. Well, On the other side of the diagram here, we have the mathematicians. And in the mathematicians, there's a subset who are the cryptographers. Now, the cryptographers are very specialized mathematicians, and they specialize in numerical methods to obscure data and make it difficult for somebody who you don't want to read it to look at it. Cryptographers are very, very important in this time because cryptography is a munition, or used as used as a component of warfare. And there's a lot of warfare going on, so you have a good amount of cryptography. And some of the cryptographers were actually soldiers, and some soldiers were drafted into cryptography if they showed a mathematical bent, and all part of this whole global brouhaha that's going on. And of course, you always have spies, and spies are, some of your soldiers are spies, some of your spies are soldiers. You even have spies who are politicians. The politicians don't like to think about that very much, but it does occur. So we have this special group of cryptographers working in the military for military purposes. Lots of information that goes on among and between soldiers you don't want your opponents to see, or even your politicians sometimes. So we have this group here, which are the military intelligence community, or at the time they would call that the security community. Now, about this time, there's a major development that actually has a very important impact on the development of the world that we live in right now. And that is that the cryptographers started making machines to help them with their cryptography. The famous Enigma device that the German army used to transmit information was an example of a mechanical one. But code breakers started to create machines that would actually help them break codes that were being used to protect information. And these were the first actual serious users of what we would call today a computer. So what that's saying is that the computer community began in the security community. Maybe not what a lot of people want to hear, but very, very important to the advance of the security community and the computer community. So just a little bit later, getting to about 1950, we have our cryptographers. They're using their computers to do their cryptographic encoding and decoding. But we also have a bunch of people who are experimenting with digital electronics. Analog electronics have been around for quite some time. Radio signals, Morse code, voice signals, even primitive television. Not to say that it ever got over being primitive, but these are people who are doing research into what you can use digital electronics for. And they discovered that one of the things you can use digital electronics for is calculations. And they're getting all excited about this because now they can do calculations much faster than they've ever been able to do them before. If you've ever seen a picture of a Babbage engine, which was a calculating machine, the intricacy of the mechanics of that are prohibitive in a mass kind of production. But with the electronic one, they could do their digital computations and everything. This was really great. Well, of course, you can't do this under government-funded grants at a university without the cryptographers noticing it and saying, "Hey, we can replace some of our analog mechanical devices with electronics, and we'll bring these people into our community." So now we have an expanding cryptographic community that includes digital, electronic, as well as their mechanical things, and the community is all very happy. And this is about the state of the computer community until about 1955. In 1955, IBM introduced the Series 700, which was the first commercially viable and commercially accepted electronic computer. And all of a sudden, we had this enormous computer community, and only a small subset of it was the cryptographers. And at this point in time, one of the most important things about security and about computers is that security means cryptography in the computer world, because that is the derivation, it's where it all came from. Anytime you're talking about security in the computer world, you're talking about cryptography. It's not like you've got a bunch of people, what you've got, and up until about 1969, what you've got is a bunch of isolated computers. The community involved is sharing stories about how their computer failed or how they come up with a new program. But there's a little bit of communication, some articles and some in journals, but really it's pretty well isolated. There's not a lot of communication between computer users. These are expensive they're expensive devices, and and it is a privilege to be able to actually use one. And then in 1969, they introduced ARPANET. ARPANET was the first major computer network. It allowed U.S. Department of Defense contractors and especially grant holders to exchange information and to provide that information, make that information readily available to the funding government agencies. And this was a major advance, because instead of computing in isolation, collaboration was now actually something you could do electronically. Now, what was important to the ARPANET, though? It's like, ARPANET is kind of a new thing. Well, consider that the backbone of the ARPANET was 56 kilobits. And that if you were trying, 50 kilobits, that's about the same speed as the DSL line that I'm giving this presentation over. And to connect to the ARPANET, you would call it on the phone. And that might mean a rotary dial. And you could get anywhere from 300 to 9600 bits per second on the phone line between your computer and the backbone. And you were paying tolls for the telephone calls. Now, in 1969, phone calls were not cheap. We think of phone calls now as being essentially free. They weren't. They actually cost real money, and you had to do real accounting on that. So what really was important to the ARPANET and to making the ARPANET work successfully was speed. You had to have fast data communications. You had to do everything you possibly could to get the bits from your machine to the ARPANET as quickly as possible so that you could hang up and save some money. And so in support of this, the Internet Protocol was developed. 5-layer stack with applications at the top and hardware at the bottom, and several interesting divisions in the middle. That was optimized to make the process of getting the information from here to there as fast as the hardware would allow it to do. Now, security, again, security talk, right? Well, you had a private government network. You weren't allowed to use the ARPANET unless you had a DoD, Department of Defense contract that you were supporting. You had unique identifiers. You were calling it on the telephone. Your telephone number was available. If your telephone number was available, and the Internet Protocol is originally conceived, you bought your your IP address. You paid money for it, and it could be tracked back to you. All right, and because we're security and security means encryption, we're going to bolt. We have mechanisms to bolt encryption on the bottom. So if you want to hook up your device to another device, you can put a cryptographic encoder between them. If you want your application to talk to the other application on the end, or if you want to do authentication, you do that up at the top in the application layer, and the stack isn't impacted by it. It's perfect, completely your choice. And that works just great. Yeah, it's policed, it's maintained, and everybody's happy, right? And the people who are not supposed to be on the ARPANET, people who don't have business being there, aren't allowed on. Well, sometime around 1982, and exactly when that occurred will vary depending on actually who you talk to. The ARPANET morphed into the Internet. Now, the Internet has a higher speed backbone, very different mechanisms to communicate to it, but it's available to everybody. So the security aspects of the Internet, a little bit different from the ARPANET. First off, it's not a private government network. Everybody's allowed on. There's nobody policing it. Your unique identifiers. Well, in order to provide access to the general public and lower cost institutions, you're not calling into the backbone. You're calling into an internet service provider who is actually connected up to the backbone. And they don't want to pay for all these internet addresses that they would have to. So they've implemented protocols that cheat so that they can actually use one internet address to get to the ISP and then lie about things going out to the individual users. So you've lost also that. But the bolt-on encryption is still there. So if you want to have encrypted communications between your machine and your internet service provider, you can still do that. Nobody's doing it though. And you can do encryption in your applications, although that does make it difficult to make them generally available. So okay, the security story is not really very, very clean here. And what did this lead to? Well, first thing it led to was the cuckoo's egg. Cliff Stoll, an astronomer who was working as a system administrator, was assigned the task of finding the bug in the accounting software because they were always like 3 or 4 cents off. And after about a year's work, it turned out that what was really going on is the accounting software was just fine. It's just that there was somebody out on the internet who was contacting their machines and using them for other for purposes to which they weren't authorized. And it was difficult to track them down because, again, there's nobody policing it, and there really isn't any way to just easily tell where things are coming from. So that was the first thing here. And then the next thing that came along was the Morris worm. Mr. Morris happened to have a little program It was supposed to self-replicate slowly and see if it could find other places to go and you know, replicate itself on other computers and then find information about where it might go from there and do the same and just kind of slowly take over the entire world. Well, there was a bug in the program. There was a bug in the rate limiting that it was supposed to be doing, and as a result, Boeing it ended up just about everywhere. Now, how did this come about? Well, probably the big reason is that without any kind of identification of who's using the network, where things are coming, or who it's coming from, you have anonymity, which is touted as a very good thing, but at the same time, you don't have responsibility, which is not such a good thing. And that led to our people. Initially, we called them crackers, and then they got called hackers because people who it was assumed that people who were clever using computers were going to be doing bad things. This rolled into the term black hat, as opposed to the from the Western movies, the bad guys always wore the black hats, the good guys wore the white hats. Currently, I think we're pretty well using the term bad actor to identify this individual. But the reality is, because you can't track them down and you don't know where they are, they're everywhere. All right, so we have this horrible state of things on the internet here where the security is just kind of out of control. But fortunately, there are still people who are looking at security from a slightly different angle, and that's the angle of access control. Access control is starting to become more at this time, starting to become more and more of an issue because you've got people sharing big, expensive machines, and more and more people are getting access because more and more people are figuring out fun things to do with computers. And in some cases, people are using sensitive information. Best example of this I know of is a site where they're using a supercomputer to do weather forecasting. And weather forecasting is generally safe information for people to have. But it can be very sensitive if your Navy, for example, is doing weather forecasts on a particular location, because that might give some of your adversaries information about where that Navy might be performing, might be having maneuvers, or might be planning to do an invasion, any of a number of things. So there's sensitivity there. And again, computers are still expensive at that point. And so you've got people sharing them. So you want to have some access control involved. Now, of course, the people who are looking at access control are going to look at the state of the art of security at that point. And the state of the art is what's in ARPANET, which is to bolt the cryptography on the side. Because remember, at this point, we're still thinking that security means cryptography. Now you want to make it optional because in a lot of cases you don't really need this. If we've got one person using the computer, you don't need the access control. If you've got 10 people, you probably do. And you want to hope nobody notices, which is just kind of another way of saying you don't want it to have a lot of significant impact on the performance of the system or the usability of the system. So the obvious, if you want to do a security feature, the obvious thing to do is you're going to bolt access control on the side rather than cryptography, and then do the other things. Right? So, does this work? Well, of course, we're going to bring our security people, that is our cryptographers, in and ask them how we're going to do this. Sorry. So, and there are a variety of things. Oh boy. Oh yeah, I got ahead. You know what? I got ahead of myself here. I'm sorry. Okay, so, and we're going to, because there are different ways people are going to want to use computers, we're going to use different kinds of access control policies. We're going to make them discretionary, where you can decide who gets to look at your data. You can make them mandatory, where you don't get to decide. It's based on what clearances you might have. We're going to define that you need privileges to override the policy. And we're going to do something a little bit different. This is something that hasn't been done before, and that is we're going to ask for assurance that your system actually works the way you say it does. Now, why are we going to start doing this? We're going to start doing this because computer companies are notorious for saying, "Oh yes, our computer does that," even when it doesn't. So the people in the government are starting to say, "Fine, these are the kinds of things we want you to do in order to demonstrate to us that your secure system actually will protect the data that we consider to be sensitive." And so assurance led immediately to the notion of process-based assurance. Process-based assurance, which was manifest in the capability maturity model, just simply says that because you can tell us good things about how it is you go about developing your code and verifying your code, we're going to trust you. Relatively straightforward, but a lot of people really grabbed onto this and ran with it. So we had this community of assurance and process management people, which led to another community, which is the Agile programming community, where after several years of dealing with the government inspired notions of how you should be doing software development, there's a rebellion, kind of an anti-community. We don't want to be part of the classical assurance community. We want to do things differently. We want to do things our way. We want to interact with each other. We don't want to write big hairy documentation. We just want to make sure that the code works. So as a result of the security community coming up with process in excess, another part of the development community rebelled and created this other community, which is the Agile programming community. And that's fine. It's like, we're talking about community here after all. So back to access control. You called in the cryptographers and said, all right, how are we going to do this? We want to separate this information. We want to make it easy for people to use the computers and have their information safe from each other. And the cryptographers said, well, we've got a few issues here. The first one is that a lot of information is born sensitive. If somebody comes up with a new idea on how to make nuclear weapons explode faster and brighter, governments generally want that information to be held very secretive. But you don't think and you can't write in encrypted form. You have to have the data before you can encrypt it. And if you have the data and it's not encrypted so that it can be encrypted, then it's accessible and you've failed your access control. And then once you've encrypted it, you can't use it until you decrypt it. And there are, of course, exceptions to this. And cryptography is expensive. You want to use the most expensive cryptography you can afford to, because your adversary is going to apply as much resources they can to break it. So if you don't spend more money encrypting your data than your adversary is willing to spend to decrypt it, you lose. So that wasn't going to work. So what was going to work? Well, we're going to have put access control in the scope and in the context of an operating system or a computer system in whole. And you've got file systems and memory management, interprocess communication, and you've got device drivers, and you've got all kinds of other interesting networking, all kinds of other interesting aspects of the system that you're going to have to do something with. No simple solution. Okay, well, how are we going to go about doing this? Because when you actually look at how much it's going to be, you're going to have to be touching virtually every aspect of your system. So first thing you're going to do, of course, you're going to call in your cryptographers because they're your security people. And although they can't actually help directly very, very much, in some minor areas, but they're not going to be able to make the whole thing work. Well, the next thing, you're going to need somebody to come and give you a security model so you can tell whether you've actually implemented something or not. You're going to get some system developers. And what actually happened in the 1980s, a lot of the computer vendors went to their development groups and said, hey, who wants to work on this? And the senior people said, I don't want to work on that. That's scary. And so an awful lot of younger, less experienced developers stood up and said, this is an opportunity for me to actually make an impact. I'm going to go for this. This sounds like a really good idea. The government wanted to see a lot of validation done. So if you're going to add a whole lot of new security features, you're going to need some validators to do it. And then the question went out, well, who knows about, who's been working with this? Who's been working with these kind of security things? Who's got experience with looking at the systems from the viewpoint of the people who are going to be breaking into it? Well, our bad actors. We're going to pull them in too, because they know a lot of stuff about this that the rest of us don't, and especially we're junior. A lot of junior people here. We need some guidance. They also brought in the system administrators because everybody realized that these were the poor sods who were going to actually have to make these things work in the real world, and they're going to have. They've been fighting with the bad actors for a long time, so let's bring some of them in too. And we've got these weird people called the virus. I'm calling the virus hunters, because throughout this whole thing, you've got people inspired by the Morris worm who are putting bits of code out onto the internet, that are gathering information and sending it back to a common place and gathering information like credit card numbers and the like. And so you've got this whole industry that's popped up that's doing nothing but tracking down bad stuff out on the internet. Now, it turns out that, okay, so we've got all these people here. Well, it turns out that there's a considerable amount of overlap between the people who are bad actors and the people who are system administrators. At the very least, from the community standpoint, they share a common interest, which is using systems to which you do not necessarily have legitimate access, or defining how to identify people who have legitimate access. So there's a significant amount of overlap there. Now, the virus hunters, there was at least one company who I won't mention by name, that was notorious for finding viruses 30 days after their antivirus found viruses almost exactly 30 days after they were introduced into the marketplace or out onto the internet. So there was a lot of speculation that they were writing the viruses, putting them out, and then discovering them and charging people for the privilege. So yeah, there was a little bit of bad acting going on there. And then, of course, our system developers and our validators started working with the bad actors because they're able to see how much knowledge there was, how much innovation there was, and to be honest, if you want to actually understand and make sure that what you're doing is actually going to work, you want to make sure that the people who are good at breaking it are involved, and so that you can actually get them stumped. One of the bright spots on this, though, is one of the techniques that the bad actors have been using for a long time to break into, to figure out how to break into something called fuzz testing. All validators are looking at this and going, wait a second, we can use that to test all kinds of things, not just whether you can, whether there's a Stack Overflow in here. I can use that just kind of to wang it, to bang at the system and see what else breaks. Well, now we're using fuzz testing to find just about everything. But as it turns out, from the standpoint of the community, what we find in here is, who really is the linchpin? Who really is the binding force within the security community? Well, it turns out it's the bad actor. The bad actor is the heart of the community, in it's the commonality. It's that which brings it together. We would like that not to be the case. We would like there to be a more positive message there. But the reality is, this is where the community actually comes together. Now I'm going to pop off onto another little anecdote here. This is one of my favorite government intervention things, community issues. Why is it that the Linux community in particular is so aggressively global? Well, one of the reasons why was that early on in the Linux world, the U.S. had very strict laws about cryptography and the exportation of cryptographic algorithms. And it's applied even to open source. So technically, if you had some cryptographic algorithms and you shared them with somebody who was not a U.S. citizen, not authorized to see them, you could go to jail. Now, this is true whether you were an American citizen or not. So there was a lot of concern among European developers, especially developers of cryptography, who were starting to make them available open source. I make it open source. I go to America and I read my paper and they arrest me. Not a good idea. So that led to one of the earliest major events in the Linux world was the Ottawa Linux Symposium. It was very accessible to people in the U.S., but it was also accessible to people outside the world. And this was a globalization. It took American leadership out of the equation, made it had to be global, because in order to actually get the people who were involved to participate, you couldn't do it in the U.S. Now, I promised some predictions in my abstract, and so I should probably actually make a few. Okay, my first prediction is that the security community will remain fractious and diverse. There are a lot of things that people consider security. It's a lot of things that people consider important. And we still have bad actors out there. We have corporate bad actors. We have companies that do nothing but try to break other people's systems, both officially and not officially. And all kinds of ideas as to how security should be done. Because the computer I'm presenting on now is 20,000 times faster than the VAX 1178, than the machines that were being used at the time of the Morris worm. The security community's issues will continue to be user experience. Making a delightful user experience for computer security hasn't been achieved yet. It's one of my goals, one of my dreams, but we'll see. Performance is always going to be a problem because everybody knows that security makes things slower. whether that's true or not. And new technologies, when we go to, when somebody introduces tri-state memory, how are we going to have row sledgehammer? Are we going to have row steam hammer? What kind of, are we going to have, what kind of problems are we going to have with that? People introduce new technologies all the time without doing serious consideration of the security implications. Okay, and finally, there's a whole lot of things I couldn't get to today. Containers, virtualization, static analysis, backporting, supply chain, artificial intelligence, and privacy. Artificial intelligence and privacy are a wonderful combination. We could talk for days about that. And a whole bunch of other things that I'm just sorry I couldn't get to today. But anyway, thank you very much. I think I might actually have a time for a question or two.
Betsy, just unmute your mic, mate.
It's going to happen. I already did it once yesterday. I did it again today. Okay, so we do have a few questions. We probably only have time for one, maybe two. So the current top voted question is, what's the suggestion to the software testers? How should we validate security software?
How to revalidate?
How should we validate security software?
How should we validate security software? We should read the documentation and read first off, get the documentation. If it hasn't been written, hit people very lovingly, but firmly, to get the documentation. And then when you have the documentation as to how it's supposed to work, then you can decide whether or not it does work.
Fair. Docs are critical. All right, so we've got a question that received an awful lot of votes very quickly. What do you feel is the biggest draw for bad actors these days? And is
money.
The current approach
money?
Yeah, well,
okay.
Makes the world go round, hey? And the second part of the question is the current approach of bug bounties enough to combat those attractions?
Bug bounties are a really bad idea. Bug bounties encourage people to do two things. First off, they encourage people to go looking for things. And if they can't make enough money, if they find something and they can't make a significant amount of money exploiting it, then they can make some money on a bug bounty. The problem with bug bounties is that they encourage people to be sneaky rather than. I would much rather have people say, I'm not going to pay you for a bug. I'm going to pay you for a patch to fix the bug.
That makes sense. That makes sense. Reward the actual improvement.
That's correct.
Okay. So we are out of time, Casey.
All right.
Thanks so much. I know the audience appreciated your talk and your beautiful diagrams and illustrations.
Thank you.
So there were still a few questions left in there. Are you happy to head over to the post-talk text chat to answer
I
some
will
questions,
do that
Casey?
right now.
Excellent. So the volunteer team will copy the questions over to the post-talk chat Kaya Theater channel in Venulus. Thank you very much, Casey. We now have a very short break, everyone, and we'll be back in 10 minutes. Bye.